Hi, I'm Dr. Hay. In this video, I'd like to tell you about cyclotron motion. Cyclotron motion is motion of charged particles in magnetic fields. And it has a couple really exciting applications, including particle accelerators. So let's draw a magnetic field and a moving charged particle coming in, and let's see what happens to it. Now let's send a charged particle into this magnetic field, and we're going to send it in perpendicular to the magnetic field. So I'm going to send this charged particle, and let's say it's positively charged, and it's moving with a velocity v. That's our velocity vector, and we're going to call the charge q. Let's use your right-hand rule to figure out what the force on this charged particle is, and I'm going to use the equation where that's the velocity, that's the magnetic field, the charge, and now we're going to find the force due to this magnetic field on the charged particle. So, put out your right hands. QV, there's the first component, crossed with B, that's B into, so my finger is pointing towards me and away from you, and the force is the thumb pointing upwards here. So you can see using the right-hand rule that you should get a force up. That's this force. The force on a charged particle due to a magnetic field. Now, if this is the only force acting on this particle, let's ignore all the other forces and just consider how this particle accelerates or moves due to the force acting on it. We go back to Newton's second law. The sum of the forces is equal to mass times acceleration. Now the forces acting on a particle, in this case it's only the magnetic force, acting on a particle of mass m has acceleration a. Now we're going to find that this cyclotron motion gives us some properties about the particle if we don't know what the particle is, because it can tell you something about the particle going into this field. That's because if you continue using your right-hand rule, QV crossed with B into up. Now, in a little bit later, force has pulled it up a little bit, and it's going to start curving, and the force will take this particle in a circular path. And so this particle takes a circular path, and that's what you call cyclotron motion. Now, like I said, if this is the only force acting on this particle, the sum of the forces is QV cross B. B is perpendicular to V, V is perpendicular to B, so our cross product simply gets us QV, B, the magnitudes. So I'm taking a cross product here, and now I'm just looking at the magnitude. I'm sorry, I missed a vector sign there. But now this is just the magnitude of this equation, is the mass of the particle in question times the acceleration. If it's moving in a circle, which it is, then our acceleration is v squared over the radius of that circle. And that's because this is centripetal acceleration. You might remember that from our chapter on circular motion. So I could solve this equation for the radius of the specific motion. And you would get R equals mv over qb. So if in a particle accelerator you collide two energetic particles together at really fast speeds, and you get some particles out that you send through a magnetic field. If you don't know what those particles are, but you do know the strength of the magnetic field that you are applying to it, you can measure the radius by watching the path of the particles as they move through the magnetic field. Then you can also find information about the mass, the velocity, and the charge of those particles. So that's the radius in cyclotron motion, and that's the movement of charged particles through a magnetic field.